Hi, dear all. Now we are going to learn early concepts of atoms. In around 600 BCE, an Indian philosopher, Kanada, Acharya Kanada, introduced a system of philosophy called Vaisheshika system of Indian philosophy. Vaisheshika system of Indian philosophy. He suggested that matter in the world is made up of small particles, small unsplittable or indivisible particles that are called paramanus. Simply anus. Based on some Vedic approaches, he calculated the size of the paramanu about 7.2 into 10 raised to minus 8 meters. But the modern observation shows that the size of the atom is about 1 into 10 raised to minus 10 meter. After this, during 460 BCE, Greek philosopher Democritus suggested that matter in the world is made up of unsplittable or indivisible particles that are called atomos. In Greek, atomos means indivisible. Actually, from this word atomos, from this Greek word atomos, the now used word atom was formed. After this, during 18th century AD, John Dalton introduced atomic theory. Let us see John Dalton's atomic theory. Okay. John Dalton is considered as the father of atomic theory. Dalton's atomic theory has the following postulates. First postulate is that matter consists of tiny indivisible particles. Called atoms. Second postulate is that atom can neither be created nor be destroyed. Third postulate is atoms of the same element are identical in all respects. fourth postulate is this: atoms always combine in whole number ratio and never in fractions. Atoms combine in whole number ratio, never in fractions. Never in fractions. But modern observations or modern scientific experiments shows that all the postulates made by John Dalton may be partially correct or incorrect. Let us check the first postulate. According to this postulate, matter consists of tiny indivisible particles. But modern observation shows that atom can be divided into subatomic particles. Atom can be divided into subatomic particles like electrons, protons, neutrons, neutrino, etc. So, atom is not indivisible, it is divisible. It is divisible. Then let us check whether the second postulate is correct or not. See, according to the artificial transmutation, one element can be converted into another. For example, nitrogen 714 when bombarded with the alpha particles. You know, alpha particle is a double positively charged helium nucleus. We get oxygen 817 and proton. When nitrogen 714 is bombarded with the alpha particles, oxygen 817 and proton are produced. Alpha particles are double positively charged helium nucleus. Let us check whether the atomic masses and atomic numbers on both sides same. Okay. 7 plus 2, 9, 8 plus 1, 9, 14 plus 4, 18, 17 plus 1, 18. So, atomic masses and atomic numbers on both sides are the same. Here, oxygen is produced out of old element nitrogen 740. That is, nitrogen is destroyed and oxygen is produced. Therefore, atom can be converted into another by artificial transmutation. This shows that the second postulate is partially correct. Now let us check the third postulate. Atoms of the same element are identical. It says atoms of the same element are identical. But discovery of isotopes reveals that this postulate is partially correct. Why? See, for hydrogen, there are three isotopes, namely protium, deuterium, and tritium. Similarly, many other elements show isotopes. Therefore, atoms of the same element may or may not be identical. May or may not be identical. Now let us check the fourth postulate, whether it is correct or not. According to the fourth postulate, atoms combine in whole number ratio. Consider the compound water. Here hydrogen and oxygen are in the ratio 2:1. It's a whole number ratio. But when we take another compound like this, ZrH 1.7, zirconium hydride. Here, zirconium and hydrogen are in the ratio 1:1.7. It's not a whole number ratio, it's a fractional ratio. From this, it is clear that atoms may or may not combine in whole number ratio. From this, it is clear that all the postulates made by John Dalton are partially correct or incorrect. That's all. Element, molecule, compound molecule, and the term atomicity. See, what is an element molecule? It is the molecule formed by an element. The molecule formed from only one element is called element molecule. For example, see sodium Na, potassium K, hydrogen S2, oxygen O2, phosphorus P4, nitrogen N2, fluorine F2, sulfur S8. See, all these are element molecules. These are formed from elements, only one element. See, this is monoatomic. This is monoatomic. But this is diatomic. It is otherwise called a dihydrogen. It is a molecule of hydrogen. It is diatomic. This is diatomic. It is also called dinitrogen. It is diatomic. It is also called difluorine. It is diatomic. It is dioxygen. Potassium is monoatomic. Phosphorus is tetraatomic. And sulfur is octaatomic. These are element molecules. Now, what are compound molecules? Compound molecules are the molecules formed from compounds. So, they contain more than one element. Am I right? See, for example, water is a compound molecule formed from hydrogen and oxygen. Methane is a compound molecule formed from carbon and hydrogen. Glucose is a compound molecule formed from carbon, hydrogen and oxygen. See, these are compound molecules. Why? Because they represents a molecule of a compound and they contain more than one element. Now, what is the term atomicity? Atomicity is defined as the number of atoms in an element molecule. So, atomicity of sodium is 1. Atomicity of potassium is 1. Why? Because their molecules contain only one atom. They are monoatomic. See, atomicity of hydrogen is 2. Atomicity of oxygen is 2. Atomicity of fluorine is 2. They are diatomic. Now, atomicity of phosphorus is 4. And the atomicity of sulfur is 8. See, this is tetraatomic and this is octaatomic. See, the term atomicity is not applicable to compound molecules. We cannot say the term atomicity for water cannot apply atomicity to methane, apply to glucose and so on. It's only applicable to element molecules and not for compound molecules. Okay. We are going to study or learn calculation of molecular mass. See, how can we calculate the molecular mass? I'm going to explain some simple examples. See, question, calculate the molecular mass of water. In order to calculate the molecular mass of water, the atomic masses of hydrogen and oxygen must be known. See, atomic mass, I'm going to write here, atomic mass of hydrogen 1 and atomic mass of oxygen is 16. See, molecular mass of water is equal to, see, there are 2 hydrogen atoms, so 1 into 2 plus there is only 1 oxygen atom, so atomic mass 16 into 1 is equal to 2 plus 16, that is equal to 18. Unit is unified mass, and it is abbreviated as U, or it is equal to 18 gram per mole. So the unit of molecular mass is either unified mass or gram per mole. Both are correct. Now I am going to give you another example. See, calculate the molecular mass of ethane, C2H6. How can we calculate the molecular mass of ethane? See, carbon 12 and hydrogen is 1. So 12 into 2 plus 1 into 6 is equal to 24 plus 6 is equal to 30 U, or 30 gram per mole. That is the molecular mass of ethane. Now, I'm going to give you another question. See, calcium carbonate, CaCO3. The atomic mass of calcium is 40. And the atomic masses of carbon and oxygen given. See, molecular mass is equal to 40 into 1 plus 12 into 1 plus, because there is only 1 carbon atom and 1 calcium atom. There are 3 oxygen atoms, or 16 into 3 is equal to 40 plus 12 plus 48. That is 0 on reminder. Say 9 plus 1, 100. That is calcium carbonate. That is the molecular mass of calcium carbonate. 100 U, or 100 gram per mole. That is the molecular mass. Similarly, we can calculate the molecular mass of ammonium sulfide, NH4, twice S. See, nitrogen atomic mass is 14. See, sulfur 32, we know. So its molecular mass is 14 into 2. See, NH4 twice, so 14 into 2. There are 2 nitrogen atoms. Plus, see, hydrogen 8, so 1 into 8. Plus, sulfur 1, so 32 into 1. Therefore, 28 plus 8 plus 32. See, 8, 68. That is the molecular mass of ammonium sulfide. 68 unified mass, or 68 gram per mole. That is the molecular mass of ammonium sulfide. Let us calculate the molecular mass of another molecule. See, CaSO4 2H2O. This compound is called gypsum. GYPSUM, gypsum. See, there are 2 molecules of water in a molecule of CaSO4. These molecules of water are called water of crystallization. So, this molecule is called dihydrated. Dihydrated means there are 2 water molecules. Dihydrated calcium sulfate. See, we can calculate its molecular mass as follows. Calcium is 40. So, 40 into 1 plus sulfur 32 into 1 plus 16 into 4 plus, see, I am going to take water together. We are going to take the molecular mass of water together. We know the molecular mass of water is 18. 2 for hydrogen and 16 for oxygen. Together 18. See, I am going to take the molecular mass of water together, that is 18 into 2. So 18 into 2, that is 40 plus 32 plus 64 plus 36. See, 10, 12, one reminder, 2, then 7, 13, 16, 17, 172. That is the molecular mass of gypsum, that is dihydrated calcium sulfate. See, this is expressed in unified mass or 172 gram per mole. Okay. Yes. Now we can calculate the percentage composition. Percentage composition means we are going to calculate percentage of each elements in a molecule of a compound. See, let us see. I am going to start with an example. See, how can we calculate the percentage composition of water? Question: how can we calculate the percentage composition of water? Okay. First of all, we have to calculate the molecular mass of water. See, molecular mass is equal to, write the splitters. That is, write the mass of hydrogen and the mass of oxygen separately. It is very important. See, there are two hydrogen atoms. So, hydrogen atomic mass 1, oxygen atomic mass 16. And there are two hydrogen atoms. So, 1 into 2 is equal to 2. That is due to the mass of hydrogen. Am I right? 2 is the mass of two hydrogen atoms. Plus, there is only one oxygen atom. So, 16. 2 plus 16 is equal to 18. This is what is the splitter. So, 18 gram per mole or unified mass. Okay. Now, I am going to calculate the percentage of hydrogen in water. See, percentage of hydrogen is equal to, what is the total mass? 18. Out of 18, what is the mass of hydrogen? 2. So put 2 here. Into 100, then 400. See, 2 into 100 divided by 18. That is 200 divided by 18. That is 11.11. This is the percentage of hydrogen. Now, percentage of oxygen. We can calculate the percentage of oxygen. See, the total mass of water is 18. Out of 18, the mass of oxygen is 16. That into 100, you will get the percentage of oxygen. See, that is 1600 divided by 18. And it is 88.88%. Okay. See, some of these percentage must be equal to 100. Okay, let us check. 11.111 and 88.888. See, we get 99.999, which can be rounded off to 100. Okay, yes. That's the percentage composition of water. Now, let us check another example. See, question. Calculate the percentage composition, percentage of, not percentage composition, but percentage of water of crystallization or hydration. Water of crystallization, water of crystallization or percentage of hydration means water in a molecule of gypsum, GYPSUM, gypsum. That is CaSO4 2H2O, dihydrated calcium sulfate. See, the molecular mass of calcium sulfate can be expressed as follows. Calcium atomic mass 40, sulfur atomic mass 32, and oxygen atomic mass 16. See, calcium 40 plus split. Sulfur 32 plus oxygen 4 into 16, 64 plus. See, I am going to take the molecular mass of water here, that is H2O together. And you know that it is 2 into 18. Why? Because water H2O, it contains the atomic mass of hydrogen is 2. That is 1 into 2 plus 16 is equal to 18. See, 2 into 18. Therefore, we get 40 plus 32 plus 64 plus 36. See, 40 plus 32 plus 64 plus 36. That is equal to 172. See, that we have calculated earlier. Okay. Now, out of this, what is the mass of 2 molecules of water? That is 36. So, percentage of water of crystallization is equal to percentage of hydration is equal to see, the total mass is 172. Out of 172, 36 is the mass due to 2 molecules of water, that is hydration. So 36 into 100. Therefore, 36 into 100 divided by 172. This is equal to 3600 divided by 172. And it is equal to 20.9, around 20.9. That's the percentage of hydration of CaSO4 2H2O, that is gypsum. Okay, that's